Do you know why bugs never get sick? Because they have antibodies. Anyway, so we're going to talk about networks this week. But before we kick it off, just a little bit about where we've been or going. One of the biggest concepts in data-driven decision-making is a sanity test. Just because you have numbers and evidence, always ask yourself at the end, does it make sense? And how can you tell it makes sense? Does it tell a story? If it tells a self-contained story in your explanation of the numbers, then it's sane. If it doesn't work out that way, then it probably isn't sane, and you need to go back and see what's wrong with the data. But I do that on everything that I do. When I work on a big project, I stop and then I say, okay, does this make sense? Networks. What are networks? Well, what networks are a bunch of nodes or entities. And these nodes could be people, they could be companies, they could be cities, whatever. As long as each one of these nodes is a homogeneous group in some way, it's a node. And how are these nodes connected? There are segments or flow segments that we talk about of how one connects to another. It could be through communication. It could be flow of data. And so what we're most interested in is what's the shortest path to get through a network, because the faster I can go through it, the more efficient my network is. How much what's my bandwidth? What's my maximum flow that I could put through it? And how do I minimize the cost through these systems? Here's an example of a minimum. And what I'm trying to do is minimize my cost, but maximize my capacity. Certain flows go in, certain flows go out. Ideally, they should balance. That's when you're working most efficiently, but it doesn't always work that way. You can think of these more like dependency graphs as opposed to just flow diagrams. And there's a field called graph theory. There are entire books about this stuff. I'm just giving you a flavor of it. But naturally, it's very important because a lot of the ideas in graph theory are algorithms that are actually used in computer science. And so graph theory is about that I have sources and sinks, I have capacity, and I have flow going through a system. What kind of network problems do I have? Well, transportation is a big one, where I'm going from one to another, such as suppliers of business stuff versus consumers. What if my supply is greater than my demand? Well, what I can do is introduce dummy nodes, and I can call those inventory. My system will end up balancing out. And of course, there's cost that I'm trying to keep minimum. And so based on how I set up my network, as you could see, the in and out can take many different kinds of forms. Now, when I look at network problems, pretty much comes down to minimizing cost or maximizing flow. And the integrality theorem just means that if I use integer data, then my arcs have to have integer answers. And this is referred to as the simplex method. Remember when we went from node to node to try to optimize something? Why do we care? These are problems for transportation, for data, and it's the foundation of network calculations, because when you have a network, what do you want to do when you have things flowing between each other? Can a node be unbalanced? Yeah, it can, meaning I can have more coming in and less coming out. And so that excess is what we call a residual, and we'll see the importance of residuals. However, in a physical system, the output has to be less than or equal to the input. And that's referred to as conservation. Yes, I have an error there. It should be less than or equal to. When we look at a map of a network, we can also make it a matrix. For example, 1 goes to 2, so I is where I start, J is where I'm going to, so 1 going to 2 is a 1. So when I'm talking about transportation problems, I'm just talking about directionality. I just use the value of 1, saying they're connected and 1 they're not. For example, does 2 go to 1? Well, start at 2, go to 1. Nope, it's a 0. And so the number of zeros I have in these rows tells me the degree. And this is called an adjacency matrix, because for a computer program, it's kind of tough to work with a diagram. So you can turn that diagram into a matrix. When I was an undergraduate, I was having problems visualizing what was going on in circuits. And my roommate, the guy with the 3 degrees, said to me, "Stop being such a dumb shit, Joe." He said, "All a circuit is a map of algebraic equations." And then I looked at it and it's like the light bulb came on and it's like, oh, well, that's all these matrices are. The process that we go through looks a lot like optimization programs that we were doing with Solver. And those solver programs are referred to as linear programming. We need an objective function. We have constraints. There's a range of values we can use. And we always want to do a sanity test at the end. In terms of data, what kinds of data do these network systems have? We can put them in arrays. We can put them in ordered lists. And we have lists and sublists behind that. We can have binary trees, we can have networks, we can have arc lists, and that means that you have pointers to locations that you're looking at. We've talked about adjacency matrices, and some of the things we're going to be skipping is we're not going to talk about Eulerian walks. What those are about is, remember when we were going from node to node to come up with solutions? Well, as you can see, in a very big network system, that could take you a lot of time. Lagrangian relaxation is pretty much about reducing a problem. That if I have a big problem, is there a smaller problem within it that pretty much looks like the larger problem, so I can solve the simpler, smaller problem. So it's about reduction. And multi-commodity means that I have multiple sources in my network. And so, you know those networks that kind of look like string art? Yeah, that's what multi-commodity is. Just gets into a lot more math and all. If you want to take an operations management class, they'll go into these things in more detail. So today we're going to talk about graph theory, we're going to talk about root extent inspection, and we're going to talk about the traveling salesman problem, because that's very common in terms of making data decisions. And in the next lecture, we'll start getting into machine learning. So we've already talked about deficit nodes and excess nodes, but what it pretty much comes down to is the flow is feasible as long as you make it non-negative. All of it pretty much has to add up in the end, and that's all it's saying. So when I look at flow problems in graph theory, I have a source and I have a sink. I have an objective, and that's I'm trying to maximize my output and minimize my costs. I have constraints. I have leftover capacity, the stuff I don't use. I could put that in a graph just like that. And that's referred to as my residual graph. And the value of each of those segments in there of my residuals is called residual capacity. When I look at the flow through this network, as we can see, it goes off in different directions, and I'm not going to maximize capacity. There are some things I'm just not going to use. So supposing I have a solution like this, where I have 6 out of 10, 9 out of 10. So this 9 goes here, my 6 goes 3 through this 8, 3 through this 7, which gives me 15 flowing out at the end. Now, is this network working correctly? And the answer is yes. Why? I haven't exceeded any capacities, and it all adds up in the end. It all works out. But is it optimal? No, because look at all this residual capacity I have all over the place. Now, in real systems, do you have residual capacity? Yeah, you do. And you have to have residual capacity. It's called slack. And it's because things go wrong. Systems aren't perfect. How do I solve these kind of problems? And some of these problems can get really big and complex, but they're actually pretty simple. They're actually kind of fun. And the way you solve it is something called the Ford-Fulkerson algorithm. And there's just 4 steps to it. The first is figure out an augmenting path, meaning just find a path from beginning to end, from the source to the sink. Your limitation going through that path is going to be your bottleneck, meaning the lowest capacity that you can flow. And so that's going to be your limit. Once you figure out what that flow is, then you do the math to even it all out. And then you keep repeating it until you don't have any more flow paths where you can get from the beginning to the end. So let's do an example. Here's my map. So I'm going to go from here to here. So I'm going to go from S to T, which is 11, 9, and 11. Well, what happens is, where's my bottleneck? My bottleneck is here. 9 is the lowest value in this. So I can flow 9 through here, 9 through here, 9 through here. And now I add it all up. And the way I add it all up is if I'm flowing 9 through here, that means I have 2 left. Same thing for this guy. Since this is 9 out of 9, this is all full. Again, this idea of superposition. This segment pretty much just goes away. Flow so far is 9. Now, let's do this again. I keep doing it until I can't get from here to here. So I can go 10 here, 9 here, and 10 here. But once again, my bottleneck is this 9. So I do the math. 9 out of 10 leaves me 1. This segment disappears, and I have 1 here. Well, is there a way I can get from here to here? No, there isn't, is there? I pretty much have reached the end. So when I add up the 2 flow paths, I have a flow of 18. That's it. Fun, isn't it? Okay, let's do another problem with a lot of residual capacity and think about some of the little tricks you can do. So the first path I pick is this one, which has a value of 8. So I'm using the maximum capacity of this. So it's 8 out of 10, 8 out of 8, 8 out of 10. So my flow is 8. So this segment goes away. Now, just because it's gone away and it's 0, it really hasn't gone away, and we'll see why. So now, since this is my bottleneck, if I go along this edge, 2 out of 2, so again, once again, I flow 2 all the way through. This segment disappears. Now I'm left with 8 here and 7 here. What I do is now I'm going to pick this path to go this way, and I only have 6 here. So 6, 6, 6, 6 out of 10. My third step, I'm flowing 6. So for my next step, I'm going to go along this path, where I go from 2, 2 out of 4, 2 out of 4. And so now, my chart looks like this. Now the problem is now you would say, oh, you can stop now, because there's no path from here to here. However, if you remember, I had a node segment here. I am allowed, I can't add in the forward direction, but I am allowed to subtract from it. So I'm going to go this way, which means I'm going to subtract 1 off of it. And so I can flow 1 all the way around like that. So now I've reached the end, because this one disappears. There's only 1 here. Now, can I go negative in this direction? Well, I don't have any flow in here to begin with. So I can't have a negative flow, and that's why I can't flow in this direction and take advantage of this, because that's the inherent one. However, if I have flow going through it, I am allowed to reduce it. This is what the final looks like. And so I have 9 coming all the way over here. I've got 10 splitting off into 3 and 7. I've got 6 coming up here. So as you can see, I've got 16 coming in here. So 10's going here, 6 coming up here, combined with the 3, 9. And so my total flow is 19. If you had quit here, you would have said 18, and that's actually the wrong answer. How do I know I have the best solution? Well, there's something called a minimum cut. And it's referred to as a greedy approach, because what you're trying to do is max out the system and figure out what's optimal. So what you do is around the source, just make a cut through the network. Based on this line, what is your output from this line? So this one is not on the line. And I'm only interested in output, so I don't care about this. So I've got 10 and 9, which means my maximum is 19. That's one way to check. What if I have interim conditions, such as this flow I want to limit to 7? Well, what I'm allowed to do is set up dummy nodes like that. So I'm going to call this node 4 prime. And that's one way, if you have interim conditions that you have to deal with, you are allowed to add nodes to a node. Let's see a real life example. The coal train crew. This was actually a Russian problem. And they were transporting coal between mines and ports by train. The crews are located in depots. And the question is, how do I manage these crews with moving everything along? Well, what they did is they looked at the service and broke it into segments. What are the nodes? Essentially, what are the service points? And the crews are basically arcs. The time used from start to finish. They want to minimize the resources because they don't want to hire a lot of people. My constraints are how much I can flow and when this is going to be completed. And so this is what the tasks look like. That the flow is, the crew starts out with the crew signs on, and then they have a choice between 2 tasks. But the tough thing is when task 2 ends, then task 3 starts. And so is it the first crew, or do I add extra crew members to do it? And then a crew signs off. So the big thing is task 2 splits off in 2 different directions. You don't know what's going to work. And so when you look at the number of combinations and crews and everything else, and the number of arcs that take place within that simplified structure, it comes out to be 11.5 million binary variables. So what they started doing is we had that decision point. What they did is replace that decision point right away. Instead of splitting off there, they would go straight to the third one. And so that reduced the number of nodes. And as you can see, the number of variables was reduced by a factor of 100. And so that became a little more manageable. Now, here's another type of route inspection problem, which is called the Chinese postman delivery problem. Yeah. The person who came up with that name, I don't know if it's inappropriate or not, but it was named for a Chinese mathematician. But this is a common problem for postmen, for delivery people. Amazon. And that's that you start at a place and what's the shortest distance to visit every point on the map. So the way you can calculate what that is what you do is first look at every node that has 3 points. In nodes that have 3 points, which would be 2, 3, 4, and 6, figure out all the pairs and then sum up what all those pairs are. So you have 2 connecting points and 2 pairs. So 2 going to 3, pick the shortest distance. So 2 going to 3 means I'm going to go 2 to S to 3, which is 3. Or I'm going to do 4 to 5 would be 4 to T to 5. Also, another pair is 2, 4, and 3, 5. So that's pretty straightforward. There is no other way. Now, if you notice, this map is bidirectional for the segments. And that makes sense because you can go any direction that you want. The whole point is that you, to every city. The next one is pairs 2, 5, and 3, 4. If you notice, I picked parallel segments or cross segments. And so 2 going all the way to 5 is 2 to 4, and actually to T to 5, like this. Not through this because that's shorter, so that's 6. The other distance from 3 to 4 is 6. Notice the asterisk means an indirect path, meaning going 2 to 3, I'm going indirectly because it's shorter. And so I sum up all these pairs, and I have come up with this. So the total shortest distance of figuring out this pattern is 6. Pick the smallest number one of these, and then add up the sum of all the arcs, 30. So the shortest route has a combination of 30. So when you start going through this, if it doesn't add up to 30, then you haven't found the optimal route. Another way to do these problems is you're allowed to put in parallel loops, because maybe for these short ones, you're better off on the way back doubling up on some of them to reduce what some of these lengths are. So here's an answer. It's arbitrary, but it adds up to 30. And I do end up totaling 30. But one of the keys are you have to think about, are there nodes that you want to double up on? Are there paths that you go over again? So as you could see, I go 5 to T to 5. And that's part of the path that I chose to use. So what loops do I want to repeat? And naturally what I look for are the lowest values. And so this is why I chose this loop to repeat, because as you could see, T to 5 is only. Now here's another example of the traveling salesman problem. And how many combinations do I have that I can go through with all these cities? And so it's a factorial. And it said -1. So in this case, for 5 cities, I have 24 combinations. If I have 15 cities, as you can see, the combinations get pretty tremendous. So how do I solve it? I solve it with this equation. This gets really, really ugly. So I'm not going to go through it on your own if you want to go through the math. But essentially, here's a transition table that you're looking at and the cost of each. So what I do is I plug into this equation of where I want to go in terms of G. And as you could see, we come up with this. The thing is, this is embedded because you're talking about the minimum of these two. This can be embedded into another one. So as you can see, you have all these combinations of 3, 2, 4, 3. And a lot of these values actually come out of the original table, like G31 is 6. But what it comes down to is the key concept is that you calculate through all the moves. And I'll leave it to you to go through this math. So summarizing our optimization part of this course is you learned about linear programming. There are also other linear programs other than solvers, such as Lindo or something like that, but they're all pretty much the same. We talked about integer programming. Then we went on to talk about sensitivity from those tables, min-max flow, shortest distance, maximum output, minimize costs. The salesman problem, we talked about matching from some of those other algorithms and maximizing the output. So as you can see, we covered a good number of topics, but all of those are things that you're concerned with when you're doing data analysis.